Recording in progress.
All right, good morning. I changed the OWL Chapter 5 Part 1 to tomorrow night, and I might even change to Friday night yet. We'll see what this looks like. Reminder, we're looking at a test a week from today, which I still think is doable. If not, we're going to have to pull it back to Monday. Okay. All right, let's see. We got number 9 here. We've got a person makes iced tea by adding, this should be 1,800 grams by adding ice to 1,800 grams of hot tea initially at 80 degrees. How many kilograms of ice initially at 0 are required to bring the mixture to 10? Well, this, of course, is going to be our final temperature. So here's what we've got. We've got 1,800 grams here. And this starts out at 80 degrees. how much ice do we have to add to it at 0 degrees, right? We're trying to calculate how much ice we need to add at 0 degrees. Okay, so the same procedure, Q lost equals Q gained. Now, we know that what is going to lose heat is my 1,800 grams of T at 80. So this is going to be MC delta T, and that mass is 1,800 grams. The specific heat is water, 4.184 joules per gram degree Celsius. And my temperature change is 80 minus 10, right? I want to get this to 10 degrees. Well, what's going to happen is you first have to melt your ice. You have ice at 0 degrees. So you want to calculate the mass of ice here, and you need to melt it. And when you melt ice, that involves the enthalpy of fusion. And the enthalpy of fusion for ice, let's look that up. Enthalpy of fusion for ice. What is that value? And we'll do all this in grams. Enthalpy of fusion for, where's my, oh, water, here we go. 333 joules per gram. Okay. So this is going to be 333 joules per gram. Then once this ice is melted, we need to raise it up to 10 degrees because you're going to end up with liquid ice there at 10 degrees. So this is going to be my mass of ice, and 4.184 joules per gram degrees Celsius. And this is going to be 10 minus 0. This is to heat your melted ice. So to do this, you're going to factor out your mass of ice here to solve this. So factor out the mass of ice. This is going to be in grams. You got to change to kilograms. So just factor out the mass of ice there to solve that. Okay, let's see what we got on number 10. You've got copper. What is the final temperature? So this is going to be Q is equal to MC delta T. We are adding 2.5 times 10 to the 4th joules of heat energy to a mass of 0.5 kilograms, 500 grams. And the specific heat of copper let's get this in grams. This is joules per kilogram. Let's get everything in grams. So what we would do is we put 1 kilogram up here. 1,000 grams, huh? So essentially, we're just going to take this decimal point right here and move it 3 to the left, right? 3 to the left to get joules per gram. and heat is added, if it's added, it's going to end up at a higher temperature. So here we'll go T final minus 7. And we need to get T final out of this. In number 11, we've got how much heat is in kilocalories is needed to melt 10 kilograms of aluminum, which has an initial temperature of 30 degrees. Okay, so what we need to do is we need to get our aluminum solid, which is initially at 30 degrees. We need to get that to the melting point of aluminum, which is 660 degrees. And then we have to take that to aluminum liquid at 660 degrees is what we're looking at. Yeah, we have to melt it. All right. So to do this part right here, this is going to be Q is equal to MC delta T. And delta T here is going to be 660 minus 30, right? For that part. Okay, then we need to melt it here. And that is going to be your mass, times the enthalpy of fusion. And we need to add those two together. So let's do everything. What do we got? Oh, we got calories here. So it looks like we're given calories. Let's stick with it. Let's see what we can do here. So we've got 10 kilograms, 10,000 grams. My specific heat is 0.215 calories per gram degrees Celsius and 330 degrees Celsius. Plus 10,000 grams times my enthalpy of fusion, 94.8. Okay, so that should help you out with those quiz questions. Yes. Oh, that should be 630, right? 630 right here. 630. Yep, 630. So I'll help you with those three. Let's then continue on here with our learning guide. And we left off saying that if we needed to calculate the energy of this situation where we start with ice to get steam, it involves 5 calculations. And that's the problem we are going to do right here. Example 5.3, page 590. So it says, calculate the energy needed to convert 500 grams of ice at -50 to steam at 200. Okay, so the first thing we need to do is we need to take our solid ice at -50, and we need to get that to ice at 0. Now, what is that going to involve? Q is equal to M, specific heat of ice, change in temperature. Every phase of water has its own specific heat. Here, we need to get ice from -50 to 0. So I'm going to leave a spot right here. We're going to calculate all of this in joules. So let me show you what we're going to end up with. We're going to end up with a number here in joules. We're going to end up with a number here in joules. And we're going to end up with a number here in joules, a number here in joules, and a number here in joules. And we're going to have to add them all up. All right. So in this case, we would have Q is equal to 500 grams. My specific heat of ice is 2.06. And my temperature change is going to be 50, right? I'm going to have to go from -50 to 0. My temperature change here is 50 degrees Celsius. I know my units are going to cancel out. And in this case, I'm going to get 51,500 joules. Now I have a chunk of ice at 0 at its melting point. Now I have to melt the ice, right? So this involves the enthalpy of fusion. I have H2O solid at 0 degrees Celsius. I want to get H2O liquid at 0 degrees Celsius. Oh, I didn't put an L in there. H2O liquid at 0 degrees Celsius. Meaning I just have to melt it, right? I need to add energy to melt my ice. And that is, the equation for that is Q is equal to M times the enthalpy of fusion. And this is going to be Q is equal to 500 grams. And the enthalpy of fusion for ice to melt it, there is no temperature change, 333 joules per gram. It looks like I'm keeping some extra sig figs here, but if we multiply this out, 166,500. So now I have liquid water at 0, correct? I'm going to steam. Liquid water at 0. I now have to take my liquid water at 0 degrees Celsius, and I need to get it to liquid water at 100 degrees Celsius. And this is what we calculated before. Q is equal to MC delta T. So nothing different here, 500 grams. My specific heat is 4.184 joules per gram degrees Celsius. And my temperature change is 100, right? And if I punch this in, I'm going to get 209,200. Now, you might just take your calculator and say, what are we writing all this down for? You could just calculate all 5 of these in one line, right? With your calculator. Okay. Now I have liquid water at 100. I need to convert that to H2O gas at 100. I need to boil it all the way. I want H2O gas at 100. This is the enthalpy of vaporization then. I'm going to turn it into vapor, a gas. No temperature change. So Q is equal to M times the enthalpy of vaporization. .500 grams, and the enthalpy of vaporization is 2260. It takes a lot of energy to boil water. So this answer here is 1,130,000. So now I have everything's converted to a gas at 100. I now need to take my H2O gas at 100 and I need to get this to H2O gas at 200. And to do that, this is going to be Q is equal to MC of steam delta T. Again, a different specific heat. We have H2O gas. So Q is going to be 500 grams. My specific heat of steam is 1.86. And my temperature change is 100. $93,000 joules. Again, we could just multiply these 3 in your calculator, go plus these 2, go plus these 3, go plus these 2, and you could punch the whole thing in once, right? You could do the whole thing at once. And if you do that, you should get 1,650,000 joules or 1,650 kilojoules. Oops, sorry. And if we wanted to, we could graph it something like this. Starting at -50, we did all these calculations, right? Remember, these flat lines, the temperature does not change. Enthalpy of fusion here to melt your ice. Enthalpy of vaporization here, no temperature change, flat line. To get your liquid water here at 100 to steam at 100, H2O gas, right? But 5 calculations. Okay, let's look at an owl question. I've got it labeled not so ugly owl, but it does mercury. And it gives you all this information for mercury. So let's go to the next page. We'll have to page back as we look at this. What is HQ in kilojoules for the process of freezing you want to get mercury as a solid, right? And if you're freezing, when you see that word, you're talking the enthalpy of fusion. So here's what we've got. You've got liquid mercury at negative 39 degrees Celsius. Now I'm going to look on the previous page, double check. It says its normal melting point is negative 39. Negative 39. So I'll give you all this information. So right now, hopefully you know liquids of mercury, or liquids and mercury's a liquid, right? Mercury's a liquid. All we have to do is take energy away to change this to mercury solid. And that is at negative 39 degrees Celsius. And how much energy does it take to do that? It's going to be my mass times my enthalpy of fusion. And I think, yeah, let's turn the page back. Notice Al gives it in kilojoules per mole. Yeah, okay. But no temperature change, correct? No temperature change, but it's in kilojoules per mole. So let's convert this to moles. And if we converted this to moles, this would be 200.59 grams. And then the enthalpy of fusion from the previous page is 2.33 kilojoules per mole. So if we plug this in, we get 0.412 kilojoules that we have to take away. We're cooling this down. So when you put your answer in OWL, you're going to have to put in a negative because we're not getting energy out. We have to put this energy in. We're cooling it. .412. Okay. So that's just a type of OWL question. So that gets us through chapter 5, part 1 for sure. Hopefully you've been poking around in there. Okay. All right, let's start then chapter 5, part 2. And that starts with the first law of thermodynamics, which simply says there's two ways. This is our energy. And this is a good example. This is dry ice. What is dry ice? Nothing but CO2 solid, correct? Carbon dioxide solid. I think you've all seen dry ice. If you put this into a Ziploc bag, close it up, put a book on top of it, it's going to allow us to do some work, huh? We get some work done by lifting this book. Now, what's going to happen is we're going to have energy is going to have to be absorbed by the CO2. It needs to take on energy, and it really just goes from a solid to a gas, right? Carbon dioxide doesn't melt. It goes directly from a solid to a gas. And the key word here is absorbed. So Q is going to be greater than 0. And basically what Al does in this first part is, this is my heat, and this is my work that I can get done. And the same thing, heat and work, these equations are the same. Now, it's really just this unit game that we play here. The work that we get out of this is negative. So let's look at examples of this on the next page. And I'm just going to put some keywords in here. So this is what Al does starting out. Again, my energy or my change in energy is equal to Q plus the amount of heat plus the work that gets done. And this is internal energy, which is the energy from the motion of atoms, molecules, or ions. All right, let's think of it this way. Here's our sign convention. You may see the first law written with a minus sign before the W. Al uses the form above, which requires the following sign conventions. If Q is less than 0, it absorbs heat. Think of this as heat in. This is endothermic. There is an increase in internal energy of the system. So that's my previous example. It's going to absorb heat. The carbon dioxide solid is going to absorb heat. If the system evolves heat, think of this as you get heat out. This is exothermic. And there is a decrease in internal energy. Let me take a highlighter in here. Energy is added to the system here. The system loses energy. You get heat out. If the work is greater than 0, think of this as work in. The surroundings do work on the system. An increase in internal energy. And work is less than 0 when the system does work on the surroundings. Think of this as work out. Okay. This is the beginning of OWL Chapter 5, Part 2. I've got questions right from it. So here's an example. You have ammonium nitrate, commonly used as fertilizer, decomposes explosively. When you see this word, can you get some work out of that? For sure, you should be able to get work out if it decomposes explosively. Now, is work positive or negative if you get work out? Less than 0, correct? Obviously, we get work out. We could raise that bad. We could raise a lot of things up in the air and get work out. So we know that work is negative. If work does not equal 0, is work done on the system or by the system? Well, we can have this right here is going to explode. So it's going to be by the system. System's going to explode. And work is negative and work is done by the system. Here's an OWL example. An automobile engine provides 515 joules of work. Provides work. Is work going to be coming out? You're going to get work out, right? Work out is going to be negative 515 joules. Work out. To push the pistons and generate 277 joules of heat. You're going to generate heat. You're going to get energy out, correct? You're going to get heat out. This is what your engine does. This is why you have a radiator there. You know you're going to get heat out. And if you have heat out, if we look up above, that means Q is equal to negative 2277 joules. And calculate the change in internal energy of this system. And my energy is equal to my heat plus my work. And my heat is negative 2277 joules. and my work is negative 515 joules. So for sure, I'm going to get negative 2792 joules. So you're just looking for keywords. Provides work, generates joules of heat. You're looking for keywords to tell you the sign. Let's go to the next page here. A chemical reaction is run in which 551 joules of heat are absorbed. Heat in. Heat in. Therefore, Q is greater than 0. My Q is 551 joules. The internal energy change is 405 joules. This is my change in energy is 405 joules. It wants to know how much work is done. So my change in energy minus my heat would equal my work done, right? So my change in energy is 405 joules. Minus 551 joules for my heat. So my work done is negative 146 joules. Okay. Now, what we are going to do next is we're going to calculate some heat that comes out of reactions. And the heat that comes out of reactions is called enthalpy. And the heat flow for our reaction is Q. For our heat flowing in a reaction, heat of reaction, we use delta H. What is delta H? It's the change in enthalpy. It's really just change in heat. We're going to do heat of reactions. And this is a definition of a state function, and the state function doesn't matter what path you take. The property of a system that is determined only on the initial and final states or conditions of the system, not on the path taken on going from the initial state to the final state. It's called a state function. Then your book says, who cares about state functions anyway? So I put it in here. Well, what it allows us to do is allows us to apply lab measurements to real life situation. So we can measure heat in lab. All right, let's go to the next page. So here's our reaction. We've got H2 gas, hydrogen gas, plus some oxygen gas. And notice they balance this with a 1/2. That doesn't happen very often. And we get water. It says that for this reaction, we get negative 241.8 kilojoules per mole. This is heat out as a product. Heat is evolved. Now, if you get 241.8 kilojoules per mole, notice that there's a 1 right here when I balance my equation, correct? And these are mole ratios. 1 hydrogen, 1/2 oxygen, I get 1 water. And this is in kilojoules per mole. If you had 2 moles of hydrogen, you would get double the energy out. These are the type of OWL questions. If I multiply a 2 through everything, and double it, 2 hydrogens, 2 times 1/2 is 1 oxygen. I would get 2 waters and I would double my heat energy out, correct? I would just double my heat energy out. Note the states of matter, solid, liquid, gas, matter. And now if I produce a liquid water instead of a gas, I get a little bit different value, correct? So make sure we keep track of the states of matter. It says if you reverse the above reaction, the enthalpy of reaction values would be opposite sign. So what we're saying is this: if I reverse this reaction, what would the reaction be? I would start with water, and I would end up with hydrogen gas. All I'm doing is reversing this. So water becomes my reactant. These 2 reactants become my product. If you reverse a reaction, you change the sign on the heat value. Delta H for the reaction is now going to be positive 285.8 kilojoules per mole. Okay, so if you reverse the reaction, instead of getting energy out, you have to put this much energy in. All right, here's an example. The standard molar enthalpy of combustion for propane is minus 2,044 kilojoules. What is the standard enthalpy change for the combustion of 3 moles? Well, if it's 3 moles, this is in kilojoules per mole. We're just going to multiply that by 3. And that is going to be negative 6132 kilojoules. All right, we got time to do one reaction here. This is table sugar, breaks down with oxygen, carbon dioxide, and water. You get negative 5645 kilojoules per mole. What if you had 5 grams of sugar? Well, if we've got 5 grams of sugar, (342.34 grams) in a mole. And then it is negative 5645 kilojoules per mole. And we get negative 82.4 kilojoules. Now, where are we going with all this? Next time we meet, please bring highlighters. Bring some highlighters because we are going to be doing stuff like this. We are going to add reactions together called Hess's Law. And we're going to want to keep track of what we are adding together with different colors. So next time we meet, try to bring some highlighters. What do you think? Should we break down? Should we make that homework due Friday? Okay, so I'll make you a deal now. Chapter 5, part 1. All right, we'll do Friday night. But part 2, in the beginning, it's just that kind of nitpicky sign thing. So please work in chapter 5, part 2, all then at the same time, right? There is no more quiz questions to add until Friday. And I think we're in good shape, but please do those early questions in OWL chapter 5, part 2. And bring highlighters next time we meet on Friday.